Hi there, this is Jude Socrates. Welcome to today's video where we will compute areas in polar coordinates. So in the past couple of videos, we learned how to take a polar equation and sketch the graph of that polar equation using polar coordinates. So today we will learn how to find the area of a region when it is bounded by such a polar equation. So maybe let's begin by looking or reviewing at the main example that we had in the last two videos. All right, here we are. So the equation is r equals 8 cosine theta plus 3. So we get a limaçon and it has an inner loop right here. So our second example in this video is going to be, well, if we zoom in here so that we can see it a little better, what is the area of this inner loop right here? So let me pause the video because, yeah, the polar graph might be a little bit confusing. We might have a better sense of this area if we switch back to polar coordinates. I'm sorry, to Cartesian coordinates. Okay, there we go. And I also hid the function which gives us the Cartesian graph. So we're only seeing the polar graph over here. So it's clearly symmetric. So if we look at the grid lines here, we have 1, 2, 3, maybe 4, 5. Maybe if we put this together, we'll have 6.5, 7, maybe 7.5 or 8. And then we multiply by 2. So maybe we'll get an area like 15 or 16. Okay, so we shall see if that estimate is correct. So first we need to know the science. What is the science behind finding the area bounded by this polar curve? All right, who wants pizza? So the idea is basically, let's think in terms of a circle. If we had a complete circle, and I'm only showing the portion in the first quadrant here, everybody knows that the area of a complete circle is pi r squared. Okay, so what if we cut out a slice of this circle, and it's called a sector, and the angle made by this circle, this sector, let's call it delta theta, in the same way that we call a very narrow width along the x-axis as delta x. Okay, this is reasonable because as we go counterclockwise around the circle, we call that angle theta. All right, so a change in theta will cut a little slice of pizza for us, a sector of a circle. Okay, so if the angle made by this sector is delta theta, how much of the circle are we looking at? Well, the entire circle makes an angle of 2 pi. Okay, everybody knows from basic trigonometry, one complete revolution of a circle is 2 pi radians. So the fraction of the circle, which is subtended by delta theta, is delta theta divided by 2 pi. Okay, so that's the fraction, the portion of the whole that this orange slice of pizza occupies. Well, the whole, as we said, is pi r squared. So multiply the whole by the fraction. Notice that the pi's will cancel. So we get a 1/2 and an r squared and a delta theta at the end. Okay, so this is the natural order of these three quantities. 1/2, a constant, r squared, and then delta theta. We're going to form a Riemann integral in a minute. And of course, when we do that in basic calculus, when we have a delta x, we put the delta x at the last part because that's where it naturally belongs. Okay. All right. So now here is the general problem. We have a polar curve, which is given by r equals f of theta. In our case, for example, we had r equals 8 cosine theta plus 3. And we are going to investigate the area made by that curve, bounded by that curve, and the constant angle theta equals A and theta equals B. All right, so in basic calculus, that was usually our x, our domain for x between A and B. But now A and B represent angles, which are of course given in radians. Okay, so we want to find, let's review what we did in basic calculus to find the area under a curve when our function is positive. You subdivide the interval AB into n pieces. Each piece has width delta x. How wide is it? Take the difference, b minus a, divide by the number of subintervals n. Within each subinterval from xi minus 1 to xi, pick a representative xi star. That is where we compute the value of our function, f of xi star. And that represents the height of a rectangle whose base is delta x. So the area of that rectangle is height times base, f of xi star times delta x. We add that for all the pieces, I equals 1 to n, and then we make the number of pieces n go to infinity. That turns into our definite integral from a to b of f of x dx. So we're going to do the same thing now to the interval from a to b, except this time, when we get b minus a over n, that represents delta theta, because that is our domain for theta. And that gives us, using the same notation, the separation, the angle made by a very small portion of that region, where the opening of that central angle is our delta theta. Okay, so we're going to do something similar to our subpartition. We have our first angle A over here, and then theta 1, theta 2, theta 3, theta 4, and so on. Within each subsector, we are going to pick a representative theta I star, and then that is what we are going to use to get a radius. Okay, if this is a very small opening, this can almost look like a portion of a circle where we started out with. So remember the formula for that area of a sector. We said it is 1/2 r squared delta theta. But now our radius is changing. Here's a radius, and then over here you have a longer radius. This is now a shorter radius, and maybe these two are similar in length. Okay, so as we go around the subsectors, we get different radii, plural for radius. But that's not a big deal, okay, because we're going to take a Riemann sum and we're going to take a limit as n goes to infinity. So the area of our little sector here in blue is 1/2 f of theta I quantity squared delta theta. And even if your r is negative, okay, so remember in polar coordinates, when we do the loop-de-loop, those r's are probably negative. Okay, so when we square that though, it's still going to be positive. So there we go. We're going to take these areas, we're going to form the Riemann sum, make the limit as the number of subintervals go to infinity, and this time, before it was f of xi star, big deal. Our function is now 1/2 f of theta I squared. So we can take the 1/2 out. This Riemann sum turns into the integral from a to b of f of theta squared d theta. All right. So that is the formula that, yes, you will need to memorize. All you have to do is square the function and divide by 2. That is what you integrate. Okay, so very important. You have to square the function. And yeah, what did we have in the beginning? 8 cosine theta plus 3. We're going to get the cosine squared. So hopefully you remember in one of our earlier videos, we have the power reduction formula for cosine squared and sine squared. I will remind you of those in a little bit. So for our first example, we're going to find the area which is inside what is called a dimpled limaçon, and the equation is R is 3 sine theta plus 5. Okay, so earlier we had an equation with cosine. This time it's a sine. Big deal. It just means that the orientation has rotated a little bit. So let's go to GeoGebra and see what this looks like. So there we are. I have changed it to 3 sine t plus 5. And there is no inner loop this time. And you can see why it's called a dimpled limaçon. Okay, it's like you have a balloon and you kind of like push it over here and just kind of do that. And you form a dimple here, like, you know, when you smile and there's a dimple on your cheek. So what that is that there are two twin points here. Let's zoom in a little bit, where you can see that the tangent line is vertical along these 2 points. They share the same, horizontal tangent line. And of course, over here, we have a different horizontal tangent line. So that is what makes it dimpled. It almost looks like a circle, doesn't it? Okay, so we'll kind of check our answer later when we see, okay, if we approximate this with a circle, what would be its radius? What would be its area? Okay, so let's go back to our workroom and apply the formula to find the area within this limaçon. Okay, so the formula we have to remember is we're going to square this function divided by 2, and we'll integrate from a to b. Okay, well, wait a minute. What are these a and b? Well, we have a dimpled limaçon, which kind of went like this. And of course, we don't pass through the origin, and the angles that we sweep out basically just go from 0 all the way around the circle to 2 pi. So those will be our limits. All right. So we're going to get, let's copy that, 1/2 from 0 to 2 pi. We have a complete revolution, and we are going to square this function over here. Okay, there we are. So next step, we're going to expand that so that we can integrate it. So we're going to get 9 sine squared theta. Okay, cross term, 5 times 3, 15 times 2 is 30. So plus 30 times sine theta. So let me copy this. And then we will add the last term, square 5, we're going to get 25. Okay, so that is our square. And I mentioned the power reduction formulas. So I hope you remember. And if you don't, I am going to remind you right now. For sine squared, the formula is 1 minus cosine of 2 theta divided by 2. Okay, so that is our sine squared theta. And let us expand that just a little bit. So we will have 9/2. I'll turn this into a fraction. And then minus 9/2 cosine 2 theta. Okay, so I can copy this. And I want cosine 2 theta. Okay, there you go. 9 minus 9/2 cosine 2 theta, 30 sine theta, and 25. These are constants. So 2 times 25, 50, plus 9, 59. Okay, so 59 over 2. And we have combined the 25 right there. Yeah, that looks great. Okay, so we are going to integrate this, and maybe it's going through your head that, okay, u sub integral of cosine is sine. We need u is 2 theta, du, and then take 1/2. Okay, I'm going to show you some magic. Let's use our brains. Sine and cosine are both periodic, and the period is 2 pi. All right, but remember that when you think of sine, for example, the first half is above the x-axis, the second half is below the x-axis, and those two areas are the same. Okay? Essentially, the same thing is true about cosine, except that the little part on the left and the little part of the right combined to have the same area as the part on the bottom in the middle. Okay? So they still cancel out. If you integrate cosine from 0 to 2 pi, you will get 0. Except we don't have cosine theta, we have cosine 2 theta. What does that 2 do to the period of cosine? Normally cosine is 0 to 2 pi. But because there's a 2 there, the period is now half, which is pi. So that just means that you're drawing the graph twice. Okay? But each part, the positive part cancels with the negative part. Okay? So those integrals are simply 0. So therefore, when we expand this out, we will expand it into 3 parts because we have 3 terms. Okay, so we'll do this plus this. I'm going to make 3 copies, and let me get over there, and let me delete along the way. So this is 1 part, and then the second part is the minus 9 halves. So let me put the minus over here, and you'll have only that part. And the last part is the 30 sine theta. So let me make 1 more copy, and we only need the 30 sine theta part. Okay? See what I did there? 59 over 2 by itself minus 9 over 2 cosine theta, 2 theta by itself, plus integral for 30 sine theta by itself. Okay? So what I'm saying was each of these, we don't even have to bother because we're integrating for a full period from 0 to 2 pi. So those will just be 0. Okay, so which means that the only survivor is the first integral, this part. And of course, we only have a constant over there. So integral from 0 to 2 pi, when we integrate, we will just get 59 over 2 theta. And the limits will be from 0 to 2 pi. Aha. And of course, yeah, if you don't believe me, well, would you believe Maple? So let me copy this down here. And Maple doesn't like these brackets. It's got to be without these brackets. And oh, brilliant Maple, what is that integral? It's 0. Believe me now? Okay, so there you go. And of course, this one is also going to be 0. Okay, so what have we got? 0, that goes away. And we simply have 2 pi for theta. And so we delete that. And we can delete all of that. So we get 59, 2's cancel, 59 pi over 2. And that is, let's see, delete this. And we will delete that. Okay, there you go. We get 59 pi over 2 as our exact area inside that limaçon. What's our approximation? So it is approximately 92.67. Okay, so that's believable. Okay, we got something that was not exactly small, so that's not a very unreasonable answer. Okay, so I was saying, it kind of looks like a circle, doesn't it? If it were a circle with this area, what would be the radius of that circle? Okay, so I'm saying, if this were pi r squared, let's call it capital squared, okay? If it were like that, what would be the value of r? Okay, so we're going to use that just to draw a circle, just for fun, and see, okay, do these two regions kind of have the same area? Okay, so solving for r squared, we get r squared equals this number divided by pi. And yeah, I don't need this stuff anymore. So this is approximately equal to 29.5. Ooh, interesting. And then we take the square root. So r is approximately, I'm just going to use the equal sign, square root of 29.5. And we get approximately 5.431. Okay, so let's go back to GeoGebra. And we're going to draw a circle of radius 5.431 centered somewhere along the axis of that limaçon. All right, so I would like to make the circle overlap the limaçon as much as possible. Okay, the high point here is at 8. Here it's at 2. That's actually negative 2. Yeah, you don't see the minus there. So that distance is 10. So the midpoint will be at 5. Okay. Wait, did we do that right? I'm sorry. No, I added. 8 minus 2 is 6 divided by 2 is 3. Yeah, that's 3, not 5. Okay. So we'll center our circle over here. So we will have x squared plus quantity y minus 3 squared equals, our radius is 5.431. 5.431 quantity squared. Ooh, there's our circle. Okay, so are you convinced that the area inside the black circle is about the same as the area inside the red limaçon? Okay, so of course, it's not perfect. Part of the circle is sticking out, but part of the limaçon is sticking out. And there's more of the circle sticking out over there. Maybe we can lower the center a little bit. Would that convince you a little better? So instead of 3, let's try 2.8. Would you be better? Ooh, okay. I think it looks better. Let's try 2.6. 2.6. Let's try that. Oh, I like that. So now our circle is over here, and there is still some part of the limaçon sticking out, but there is some part of the circle which is sticking out here. So would you believe that this region plus this region equals the area of this region? That looks pretty reasonable. Okay, so I hope that convinced you that our answer, which was what, 59 pi over 2, is a reasonable answer. Okay, so now let us find the area of our inner loop in our limaçon with an inner loop. All right, so our second and final example, we want to find the area inside the inner loop of this limaçon. So this time, we're no longer going to go from 0 to 2 pi. In fact, that doesn't make sense because we're going to go around here, and then we're going to pass through the pole, and then around here, and then, yeah, there's really no good geometric interpretation of the full integral from 0 to 2 pi. In fact, let's think about that for a minute. If you only go from 0 to pi over 2, that's over here, right? You would be getting the area of this region, which includes that inner loop, okay? And then when you go from pi over 2 to maybe this angle, you will get the area of this little sliver of that limaçon, okay? So it's really, yeah, it really doesn't make sense this time to go from 0 all the way to 2 pi. What we want to do is, we want to go from the angle where the inner loop begins up to the angle where the inner loop ends. So if you recall, we looked for those angles in the first video. We said, when is r equal to 0? Oh, we can see that over here. You want cosine theta to be -3/8. You remember that? We got this angle in the second quadrant. Okay, now here's something smarter. Because we have a cosine there, this curve is clearly symmetric across the x-axis because we have eyes. We can see it, right? But also because if you plug in negative theta, you get the same thing as cosine theta. So the r over here is the same as the r down here. Okay, so what does that mean? Instead of going from inverse cosine -3/8 to, what was it? 2 pi minus inverse cosine -3/8. Why don't we just go halfway, right? Exploit symmetry. So we go from this beginning angle to halfway. Now, what is this halfway angle? That's not 0. That is on the left side of the circle, which would be pi. So remember, if theta is pi, we can see it here. Cosine pi is -1. So we get -8 plus 3, -5. That's why we are at 5 over here. And you might say, wait, that's +5. Pi is in this direction, going to the left. But since r is -pi, we go backwards. And it is in the positive x-axis direction. Polar coordinates are a little bit crazy, don't you think? Okay, so in this case, we will just go from the angle where the loop begins up to pi, and then we will multiply our answer by 2. Okay, back to the workroom. All right, so here is our problem. We want to find the area of the inner loop of r equals 8 cosine theta plus 3. And these are our notes from our previous video, the first one. To cross the pole, we need r to be 0. I mentioned that a few minutes ago. So cosine theta is -3/8. So using our inverse cosine function, the first angle is alpha, r cosine -3/8, which is in the second quadrant. And then we reflect that over to the third quadrant by subtracting alpha from 2 pi. So 2 pi minus r cosine -3/8. Okay, so this is our formula for the area, but we said instead of starting at alpha and beta and finishing at beta, we will do the smart thing and we will double the area. So 2 times 1/2, which of course cancels to 1, but I want to write it down anyway. And we will begin at this angle, r cosine -3/8, and we will finish at pi, okay? Because trust me on this, you don't want to plug in 2 pi minus r cosine -3/8, whatever antiderivative. We're going to 5 over here. That's just crazy. So we are going to square this and integrate. Okay, so it's going to be a lot like our first example with sine theta, except you get to review our formula for cosine squared. Hint, instead of minus, it's plus. Okay, so now we get to expand, and of course, 2 times 1/2. Goodbye, that is simply 1. Okay. 8 squared, 64 cosine squared. 3 becomes 9. And in the middle, don't forget there's a middle term. 8 times 3 is 24, times 2, 48 cosine theta. All right, and that is already squared. Excellent. So now we are ready to reduce, power reduce. change the cosine squared into, oh look, a 1/2. Thank you very much. That will be 1 plus cosine 2 theta. I'm going to borrow u and double u. I'm paying interest. Okay. So cosine squared is 1 plus cosine 2 theta divided by 2. Excellent, and that is really good because 64 is divisible by 2. So we are left with 32 down up here. And we get to multiply that to the numerator, 1 plus cosine 2 theta. No more fraction, yay! Okay, 64 over 2 is 32, 1 plus cosine 2 theta. Nice. Keep going. No, not all the way, just the last line. And expand, and you get 32, and 32 cosine 2 theta, 48 cosine theta plus 9. Okay, very nice. 32 plus 9 gives us 41. Okay. Excellent. So this time, yeah, we're going to have to do a little u substitution there. U is 2 theta, so du is 2 d theta, and d theta is 1/2 du. The integral of cosine u is sine of u, not negative sine of u. Okay, did you get all of that? Try doing it in your head. I dare you. Pause the video. Try to do it in your head and see if you can come up with the same answer we have. Okay, so integrating now, we're gonna get 41 theta. And this becomes, there's a 1/2, so that's 16 sine 2 theta. And the integral of cosine theta is sine theta. We just did that. And our limits go from arc cosine minus 3 over 8 up to pi. Okay, so we have done the integration. Okay, so quick review. Okay, the best way to check if your antiderivative is correct is to take the derivative. What's the derivative of 41 theta? 41. Derivative of 16 sine 2 theta, chain rule. 2 goes out, 32. Derivative of sine is cosine, 2 theta stays in sine. Correct. Derivative of 48 sine theta is 48 cosine of theta. Okay, excellent. So that antiderivative is done, but we're going to plug these angles in. Okay, easy enough for theta and for sine theta, or is it? Or is it? So remember that we kind of did this, I believe, in the second video, or basically our previous video, where we were looking for horizontal and vertical tangent lines. And we said, oh, if the cosine is minus 3 over 8, what was the sine? We did something like that. So the cosine is minus 3 over 8. So think of it as, what is cosine? It is adjacent over hypotenuse. Okay, so the adjacent is minus 3. The hypotenuse is 8. So the opposite is square root of 64 minus negative 3 squared minus 9. Yeah, I remember this because I wrote down 5 instead of 55. Silly, silly, silly. So we get square root of 55. I will not make a mistake this time. Okay, so the sine of this nasty angle, and it's in the second quadrant, so sine is positive. It is positive opposite square root of 55 divided by 8. Okay? And we're going to need that because, oh yuck, we have sine 2 theta. But we know our double angle identities, don't we? So we get sine 2 theta is 2 sine theta cosine theta. Remember that? Okay. So that is our double angle identity. And sure, let's simplify that coefficient to 32. Oops. 32. Okay, exciting. We are now going to plug in the endpoints to each of these terms. And we will need the values from there. I knew that would happen because we have exceeded the maximum capacity of this screen. So I'm going to shrink it to 150. Okay. So one at a time. Okay, we're going to plug in these endpoints. No need for the brackets anymore. So for theta, we will just get pi minus that angle, our cosine of negative 3/8. Okay, now we will plug in sine theta cosine theta. Okay, but for pi, sine of pi is already 0, so goodbye, 0. Carefully now, plug in sine theta and cosine theta for this angle. Okay, so cosine theta is negative 3/8 because of the cancellation rules. Cosine of arc cosine minus 3/8 is simply minus 3/8. But the sine is square root of 55/8. Interesting. Okay, and how about for 48 sine theta? At pi, sine of pi is, 0. And then at the lower limit, we know the sine is square root of 55/8. Yes. Okay. Very nice. There is nothing we can do about the first term. It is what it is. But let's see, in the second one, we have minus minus. So that's just plus, isn't it? Okay. And yeah, that's a minus. Yes, so it's going to be a minus 48 times that thing. Okay, let's keep going because there's a lot we can cancel, don't you think? We have 8 times 8 here, that's 64, cancels partially with 32 to give us 2, right? So the 32 goes away, the 3 is going to stay, 8's going to go away, square root of 55 is going to stay, we're going to have 2 left in the denominator. Check, 3 square root of 55, 32 divided by 64 is 1/2. Okay, last one, 48 divided by 8 is 6. Minus 6 square root of 55. Whew, okay. So, oh, look, check it out. We have 2 expressions that have square root of 55 in it. So we can combine them. 3/2 minus 6. 3 minus 12 minus 9/2. So let's put that together. Minus 9 divided by 2. Yeah, there you go. Whew, that is the exact area of that inner loop. And keep your fingers crossed because I want to see if this is positive or negative. Oops, I just remembered that GeoGebra does not like brackets when we're not dealing with a matrix. It wants, I'm sorry, I meant Maple. It wants parentheses. Okay, keep your fingers crossed. Thank you. That is a positive number. So it is, well, positive is good. Remember how we checked that the circle of that radius that we figured out is reasonably overlapping with that limaçon. Okay, let's see if we can make sense of this area. It's 15.27-ish. Okay, let's go back to GeoGebra. All right, so can we draw a circle to kind of approximate this loop? Well, we can try. So the area is 15.27. So again, pi r squared. So divide by pi and take the square root, right? So square root of 15.27 divided by pi. And we are gonna get 2.2. Okay, so that's the radius. Oh, 2.2 times 2 is 4.4. Ooh, very good. So it's gonna be, yeah, it should be pretty close. So yeah, that's 5. Let's just center it at 2.5. Okay, so x minus 2.5 squared plus y squared equals 2.205 quantity squared. Oh, okay, there you go. Not too bad, don't you think? Okay, so again, some of the circle is sticking out and some of the limaçon, the inner loop, is sticking out. So I hope that convinces you that the answer that we got is correct. Okay, there you go. So that's our video. I hope you enjoyed it. And until next time, I hope you enjoy the rest of your day. Bye.